Right now, in Victoria Harbor, a cargo ship is sailing directly above a speeding train. Both are moving through the exact same patch of water at the exact same moment. One on the surface, one 30 meters beneath the seabed, sealed inside 11 concrete boxes that each weigh more than a small naval fleet. Nobody on that ship has any idea a railway exists underneath them. For 43 years, Hong Kong's East Rail Line simply stopped at the edge of the harbor. 500,000 commuters a day hit that same wall and had to switch to something else to finish their trip into the city. Building a tunnel to finally connect it meant threading a new crossing between 5 tunnels that already existed under that same stretch of water, drilling through a live financial district and, as it turned out, surviving a construction scandal that nearly shut the whole project down. Here's how it actually got built. Building a tunnel on dry land. You can't easily dig a trench across one of the busiest shipping lanes on Earth without shutting it down for years. So engineers didn't build this tunnel in the harbor at all. They built it in a quarry. 11 massive concrete sections, each roughly 23,000 tons, were cast on land behind a temporary seawall, over roughly 2.5 years of continuous work. Getting the casting bed level enough mattered enormously. Even a few hundred millimeters of unevenness across a 160-meter section would have doomed the whole element to permanent misalignment once it was in the water. Each pour ran for 36 hours straight, with thermal sensors embedded in the concrete, watching for any cold joint that could compromise the structure, and waterproofing checked down to the millimeter, because a single gap in the seal would let the harbor flood the finished tunnel in minutes. Once a section was finished, the temporary seawall came down, the quarry flooded, and 23,000 tons of solid concrete did something that sounds impossible. It floated, threading the needle at night. Each finished tunnel section then had to be towed out into an active 200-meter-wide shipping lane, an 18-meter-wide slab of concrete navigating between commercial vessels, almost always at night, tracked to the centimeter by GPS towers mounted on its roof and guided into position by a team of tugboats. Before it could be lowered, engineers had to cut a precise trench through 30 meters of harbor silt and screed a gravel foundation flat underwater using lasers with a tolerance of just 20 millimeters. Because getting that base wrong meant a permanently tilted 23,000-ton tunnel section. During one of these operations, a cargo ship's anchor dragged across the prepared bed and disturbed it just before an element was scheduled to descend. The team aborted mid-descent, held the massive structure suspended at 15 meters for 4 straight days, while the seabed below was re-leveled and reconfirmed, then resumed. Once each section landed, a rubber gasket compressed between it and its neighbor under the sheer water pressure of the harbor above. That compression alone forms the watertight seal, holding the whole tunnel together, backed up by a second seal fitted from the dry side once the joint was pumped clear. Drilling under a live city. While the harbor crossing was being floated into place, a separate fleet of tunnel boring machines was chewing through the ground on land, through granite, through hundreds of old building foundation piles directly in the planned path, and, in one case, straight into an uncharted concrete raft nobody had recorded anywhere, which jammed a boring machine solid for over a week until crews could grout around it and restart. Blasting through granite this close to the surface meant calculating explosive charges precisely enough to avoid damaging buildings just 10 meters overhead, with hundreds of vibration sensors on nearby structures set to halt blasting instantly if a single reading crossed the safety threshold. Then, beneath one planned station, crews hit something nobody had planned for at all. A 900-year-old Song Dynasty archaeological site sitting directly in the excavation path. The station had to be redesigned around it, shifting the entire structural grid 3 meters sideways to preserve a centuries-old well, engineering losing that particular argument to history at a cost of months of delay. The scandal that stopped everything. The most serious crisis wasn't geological at all. During construction of new platforms beneath an existing live station, an inspector found a rebar coupler, a connector critical to holding a 30-meter deep support wall together, that had been left disconnected inside a section of wall that was already carrying the weight of a functioning railway above it. He kept checking. He found nearly 2,000 more. Investigators determined that in some sections, short lengths of steel bar had been dropped into wet concrete without ever being properly connected, then simply poured over and buried, leaving a structural wall supporting live train loads with a meaningful percentage of its connection system effectively missing. The Transit Authority halted all concrete pours across the project and launched a full investigation into every wall built under similar conditions. Fixing steel connections buried inside already hardened concrete isn't something you can undo, so engineers built an entirely new steel support frame to bypass the compromised sections, rerouting the structural load of the trains overhead onto beams that had nothing to do with the original defect. Roughly 650,000 tons of rock had to be removed to install that fix underneath a station that never stopped running trains during the day, with crews working in the few hours between the last train at night and the first one at dawn. The frame itself, around 5,000 tons of steel, was welded together entirely underground, in a confined space with no crane access and no daylight. The delay cost the project years and an enormous amount of money, but the investigation ultimately confirmed the fix was safe, and work resumed. Digging beneath running trains. Even after that, the project still had to tunnel directly beneath a 40-year-old subway line running trains every 3 minutes, with tens of thousands of commuters overhead who had no idea excavation was happening under their feet. At one point, sensors detected the older tunnel had shifted 22 millimeters, dangerously close to the safety limit, forcing crews to install emergency steel props under the live tunnel in under an hour, while engineers recalculated overnight to stabilize it before it moved any further. Testing before a single passenger rode it. Once the physical tunnel was finished, nothing about it actually worked yet. Track had to be laid across a structure that had already been sitting on the harbor floor for a year, followed by months of reconfiguring the automated signaling system that controls every train. Because if that system fails, no train moves, ever, by design. Engineers ran the tunnel's high-voltage systems through a 72-hour continuous live test across 5 kilometers of tunnel, then operated empty trains through it daily for another full year, deliberately stressing every system to catch failures before a single paying passenger ever boarded. Groundwater sensors placed around the harbor crossing kept watch for anything that might indicate a seal had started to fail, including small, unexplained daily shifts in a couple of sensors that engineers monitored closely right up until certification. What finally opened wasn't just a railway. It was roughly a decade of drilling through undocumented obstacles, floating multi-thousand-ton concrete boxes across live shipping lanes, and recovering from a structural scandal that could have ended the entire project. Every train that now crosses Victoria Harbor in minutes is running through a tunnel that very nearly didn't survive its own construction. Which part would you least want to be responsible for? The floating tunnel sections, the archaeological redesign, or fixing rebar buried inside a wall already holding up a station? Let me know in the comments.